Well, hello. I hope everyone can hear me. Could hear my voice. My name is Dr. Ehsan Sharif Pagala, and thank you for joining on this evening local time here in Iran. And it's a pleasure to have our first international speaker as Professor Habib Zaidi for today's evening and afternoon, where Professor Zaidi is. I would actually kind of request if all of the audience could make sure that the microphone is switched off and also the webcam is switched off. And in case if they want to ask any question, feel free to ask your questions towards the end of the session when we have our question and answer session. And then, so first we would be having the talk by Professor Habib Zaidi, and Professor Habib Zaidi, I will introduce him a bit later on. But before that, we were trying to have Professor Zaidi to present his amazing research and findings at the TPCF Preclinical Imaging Symposium a few months back. And so back then, due to some technical difficulties, we were not able to have his talk, and so therefore we asked him if he could actually be the first international speaker for TPCF webinars. And I don't know if Professor Zaidi, if you're around, I would like to first introduce Professor Zaidi. So Professor Habib Zaidi, he's a chief physicist and head of the PET instrumentation and neuroimaging lab at Geneva University Hospital, and also he's a faculty member at the Medical School of Geneva University. He's also adjunct professor at various different international top universities around the world, including here at Shahid Beheshti University in Iran and also Tehran University of Medical Sciences. It's an honor to have you, Professor. I don't know if you could hear me. Yes, I can see your beautiful video and I could see you smiling.
Very good.
So with that, I would like to give the microphone to you, and so we would have some question and answers towards the end. Once again, if I could ask all of the audience to switch off the webcams. I can see someone called Aisuda Ziai something. If everyone could switch off your webcams, that would be great. Because we don't want to be distracted by the videos, and we just want to be focused on the presenter. And I will also switch off my video, and towards the end, I will switch it on to run the question and answer session. Professor Habib Zaidi, thank you very, very much for accepting our invitation for tonight, and it would be an honor to have you as our first international speaker of the TPCF webinars. Thank you very much.
Very good. Excellent. So good afternoon, good night, or good evening. So can you hear me?
Yes, loud and clear. Thank you very much.
You can. Okay, very good. Excellent. So let's get started. Yeah.
If possible, I don't know
So
if
just
the
need
webcam is
to.
switched on or not. Sorry to interrupt. If you could also switch on your webcam, that would be amazing as well. So
I'll try to. So just give me a chance to share my screen first.
yes, I
Can
can
you
see
see my
your,
screen right now?
yeah,
Yeah.
I can see
Okay.
your
So let me.
presentation. Yeah.
Very good. Excellent. So let me just put this aside here. Okay. So just to move this a little bit here on the right side. Okay, very good. Mm, So anyway, so most of the research that I'm going to present, so very quick overview of the technologies I'll be talking about. And then, so the research that I'll be talking about was mainly done in collaboration uh, with the groups based in Iran, with a few exceptions, of course, for some of the works that have been done essentially here. So for those of you who have never been exposed to hybrid imaging technologies, so probably know the principles of sequential PET-CT imaging. So you obviously need to have access to an X-ray tube and detectors on the opposite side, and then you perform a scout scan, and then you define the axial field of view, get spiral CT down, and then based on this, you build an attenuation map, and then using the same batch, you just push the patient towards the PET detectors located bit off-centered, so almost 60 centimeters or a little bit more than that, depending on the scanner manufacturers, and then you get the PET images, and then the fusion of the two that you present to the MDs for clinical diagnosis, therapy planning, or monitoring of treatment whatsoever. And then more recently, so we have witnessed also major developments in hybrid imaging technologies combining PET with MR. So what you see here is basically the Ingenuity PET MRI system with the time of flight, Gemini time of flight, and the combined with the Achieva 3 Tesla X-ray series. And so it's a sequential acquisition with alignment PET and MR images at the end. A number of such systems were deployed worldwide, and we're happy to have, or proud to have the first system installed in our facility about 10 years ago. So the first one in Europe and the second worldwide. So the design concept of the concurrent brain PET MR developed by Siemens in collaboration with the group in Tübingen was further exploited to build the Siemens Healthcare Biograph MMR, which used avalanche photo detectors, which are MR compatible. And this also device has been installed in a relatively large number of institutions. And more recently, so GE came up with their Signa, which uses silicon PMs. So they have the capability, they're extremely fast and have the capability uh, to be to operate with time of flight technologies. And more recently, so this a Chinese company called United Imaging. So we'll be talking about this again. So the next few slides, they also get their UPMR 790 HD time of flight approved by the FDA, and they're commercializing this device. So just some of the images that we can expect. I'm aware that PET-MR is not available in Iran, but just to give you a sense of what to expect in terms of image quality. So excellent soft tissue for the brain, and obviously the fused images gives you additional information that you cannot get through separate acquisitions. And again, for the myocardium, so through the gated images, so the myocardium is better defined and differentiated, as you can see from this example. So as kind of research the trend, so which is being also used, and I guess AI is going to play a major role in this type of devices in the near future, is the so-called total body imaging device. So the idea is not new. So a number of investigators have proposed different design concepts, but the group of Simon Scher was the first one to get funding, actually about $60 million from the NIH in the States, to build the very first device in collaboration with this company that I just named it called United Imaging. And you see the principal investigators, Ramzi Badawi, Simon Sherry, and Terry Jones, very proud of testing the system in Shanghai, so using a 2 meters long cylindrical phantom to test the performance of the system. And just to show you some of the images that have been recently published in Journal of Molecular Medicine last year, and more recently, you see this nice dynamic image. So immediately starting after the injection of the tracer. So in terms of static imaging, obviously can decrease the acquisition time to a few seconds to get a reliable static scan. And then you can also perform dynamic scans for to be able actually to do parametric imaging using compartmental modeling. And so the authors actually recently developed a new method using only the first 90 seconds of the post-injection scan data with the total body system that they have developed, demonstrating the capability of this total parametric imaging and kinetic parameter estimation bidirect, and kernel reconstruction techniques. So getting to the point of today, so artificial intelligence or AI started in the 40s, so it's not really new. And different algorithms were developed during decades. So after passing from dark ages, thanks to the data availability and GPU computation, in 2012, it raised again with deep convolutional neural networks, and there are basically two major winters. So in 74, 80, and then again 87, 93, if my memory is good enough, and several small episodes, including the following. So for instance, 1966, there was the failure of the machine translation. In the 70s, the abandonment of connectionism. And then there was a period of overlapping trends later on in the 70s, and we're happy that interest in this type of technologies was revived again. So I'm not going to give you the full history of this development, but let's get to the essential here. So since the watershed moment of 2012 and the subsequent success of deep learning algorithms outperforming other competing classification algorithms on the Google ImageNet database, there has been a rejuvenated interest in artificial intelligence, and particularly deep learning in multimodality medical image analysis in particular. So learning can be either supervised or semi-supervised or unsupervised. So most of the algorithms, they use the supervised technique, and I'm going to tell you why later on. And obviously, machine learning, as you can see here, is a subset of AI, which can be divided in three main areas. Um, Mainly medical imaging supervised learning for regression, basically image to image translation and the classification use. And deep learning is basically a subcategory of machine learning techniques that allow for image data representation, for example, feature extraction, task learning, classification or detection in the same framework. So deep learning is basically a class of machine learning algorithms that use multiple layers to progressively extract higher level feeders from the raw inputs. So for instance, in the context of image processing, lower layers might identify edges, while higher layers may identify the concepts relevant to a human, such as the digits, letters, faces, and so on. So the complexity really of the network depends on the application. So this is a nice plot actually from a very good paper published in Nature Reviews in Cancer by Hosni and colleagues. So it outlines basically the performance levels of AI and human intelligence starting from the early computer age and extrapolating into the future. And early AI came with the subhuman performance and varying degrees of success. And currently, we are witnessing narrow task-specific AI applications that are able to match and occasionally surpass human intelligence. So it's expected that general AI will surpass human performance in specific applications that need to be defined within the coming years or so. So humans will potentially benefit from the human AI interaction, bringing them to higher levels of intelligence. So from the same paper, this is a schematic which outlines the various tasks within radiology where AI implementation is likely to have a major impact. So on the left side, the workflow basically comprises the following steps: pre-processing of images after acquisition, image-based clinical tasks, which usually involve the quantification of features, either using engineered features or traditional machine learning or deep learning, reporting results through the generation of textual radiology reports, and finally, the integration of patient information from multiple data sources. So AI is expected to impact image-based clinical tasks, including the detection of abnormalities and the characterization of objects in images using basically segmentation, diagnosis and staging, and the monitoring of objects for diagnosis and assessment of treatment response, TNM, tumor metastasis, and a number of other issues that need to be quantified. So I'm not going to, this is a busy slide here showing you that basically Google. So and then lots develop a lot of stuff. I'm not going to advertise for Google, but they demonstrated in very two excellent papers published in Nature that AI technologies and computers can beat actually the experts in this famous game of Go. So deep neural networks actually managed to beat the experts in the field. So I guess in the first paper, 98% of the cases. So that's in the Nature 2016. And in follow-up papers have demonstrated that it can beat actually the human experts in almost 100% of the cases. So obviously, so the leadership became worldwide aware of the importance of these developments. And in the US, I'm not going to also make comments on the intelligence of the president of this nation, but obviously, so there are people aware of the importance of these technologies who are behind him, who realize that the importance of AI and AI so is actually one of the well-funded areas in the United States, and obviously a number of companies have created pretty large research groups focusing on this particular area, especially linked to medical image analysis developments. So this is a very nice book also by Ji Wong, so one of the pioneers in the field, and actually he reported basically the international competition in deep learning. I more that a recent survey actually pinpointed that Iran is one of the leaders in the field. So you probably know a lot about this development, but in this book, and according to uh, PubMed search, I think he performed with deep learning as the topic term, with data collected in July 2019. So the leading nations, obviously the United States, followed directly by China, and then with England, Germany, Canada, and so on. So I assume that there are some mistakes because I'm really aware that Iran is one of the leading players in the field. Probably have seen this before. So this is called hype cycles. So whenever there is a new technology introduced, so the people get very enthusiastic about it, get excited, and a lot of users and followers, and then you there is a peak inflated expectations, and then the curve comes down, kind of disappointment, and then you reach kind of plateau of productivity. So these concepts, so this company who does this, I mean, for emerging technologies, 2019, and you see that deep learning is really on the top here. So deep learning received a lot of interest and was very attractive from development standpoint. I just look it up, so the curve in 2019, and it disappeared so for some reason, but I think it's worth to show you this figure here. So deep learning, due to its unprecedented success in tasks such as image classification, has emerged as a tool for image reconstruction with the potential to change the field. And in recent years, deep learning has been applied to the city image reconstruction problem, and this is an example from one of the scanner manufacturers promoting this technology. So obviously you see major improvement in image quality. So similar to what basically has been reported when using iterative reconstruction techniques. If you look to the shoulders here, so the noise decreases significantly with the deep learning technique. But a recent PNAS paper demonstrated crucial phenomenon. Deep learning typically yields unstable methods for image reconstruction, and the instabilities usually occur in several forms, where certain tiny, almost undetectable perturbations, both in the image and sampling domain, may result in a severe artifacts in the reconstruction. Second, a small structural change, for example, a tumor, which may not be captured in the reconstructed image. And third, a counterintuitive type of instability where more samples might yield poor performance, which is really counterintuitive. So I really invite you to go through this paper and results to the issues that could be encountered in this context. A recent paper also published by the group of Lei Ching from Stanford reported on the use of patient-specific reconstruction of volumetric CT images. So the authors basically demonstrated in an elegant paper published in Nature Biomedical Engineering that a deep learning method or model trained to map projection radiographs of a patient to the corresponding 3D anatomy can subsequently generate volumetric tomographic X-ray CT images of a patient from a single projection view, which means from a single radiography, which is really astonishing. So they demonstrated the feasibility of the approach with the super uh, upper abdomen, lungs, head, and neck CT scans of 3 patients. So meaning that the study is still experimental and not validated on large clinical databases, but you can appreciate actually from these examples that volumetric reconstruction using deep learning could be useful in a number of applications, including image-guided interventional procedures such as radiation therapy, needle biopsy, and might also help simplifying the hardware of tomographic imaging systems in the future. So the editors actually of major journals such as Radiology, actually I think they were overwhelmed by the number of papers reporting on deep learning and its use in radiology and other image analysis applications. And this motivated actually the RSNA to create a new journal called Radiology AI, with the editor. You can see his name here. And in our field in molecular imaging, so both the European Association of Nuclear Medicine and the Society of Nuclear Medicine, they published a couple of special issues actually summarizing the recent developments in the field. So I just decided actually to show you a few examples from our research lab. So reporting the use of deep learning in various areas in different fields, uh, going from instrumentation to optimization of data acquisition, and then finally image analysis and processing. So this is the first paper by one of my PhD students who is originally from Iran. So the scintillation light distribution produced by photodetectors in PETs produce what we call the depth of interaction, the DOI, required for high resolution imaging. And the goal of position techniques is basically to reverse the photodetector signals pattern map to the coordinates of the incident photon energy position. And so in this work, what we did is that we used the supervised deep neural network to approximate the DOI, and we assessed its performance using Monte Carlo simulations for the configuration of a small animal or preclinical system using continuous LYSO crystals and 12 by 12 silicon PM arrays. So the centration position was predicted by a multi-layer perceptron neural network with, if I recall, were 256 units and a few layers whose inputs were the number of file pixels on the silicon PM plane. And then a Monte Carlo code was basically used to generate data sets. And just show you this results here, where you can see the PET scanner spatial resolution based on Unger's logic compared to the MLP position algorithm used in this work. Obviously, for both the axial and the radial spatial resolution, and the results obviously demonstrate that using the MLP-based position algorithm in the detector models constituting the PET scanner improves significantly the spatial resolution by, I would say, approximately 20%, while the absolute sensitivity remains constant. So without altering the spatial resolution compared obviously to the conventional Anger logic-based positioning schemes. Another recent paper by another PhD student in my lab, so we looked at actually some collaboration with colleagues from Tehran that I thank very much here for providing the data that were used in this work. So we used actually develop a concept for ultra low dose chest CT imaging of COVID-19 patients. So a timely topic, as you probably can understand. So the study aimed to design an ultra low dose CT examination protocol using deep learning approach suitable for clinical diagnosis of COVID patients. So obviously the data were acquired in full dose and then through simulations of the low dose scans, as you see from the parameters here, were simulated. And with the bunch of clinical studies, if I recall well, I think around 800, 170, and the same pairs of ultra low dose and full dose images as input for the training and test and external data sets respectively to implement the full dose prediction technique using obviously residual neural network as you can see here to generate the full dose from the ultra low dose images. And if you quickly here, so go, I can show you one example here where the algorithm so predicted quite well the full dose scans from the low dose scan, and obviously the full dose scan here on the left side is serving as a reference. So significant improvements in image quality. I'm not sure if it's going to impact the clinical diagnosis, but the full dose and corresponding low dose images actually were in very good agreement. Now, so the issue with this type of black box techniques, such as deep learning, we often have outliers. I mean, the algorithm works in 98, 99 of the cases, but it really deviates from the expected solution in some cases. And we've got an outlier here where the city images of the patients, where the deep learning algorithms, obviously, as you can see, improved image quality, but changed the patchy lesion to consolidation in the predicted images, something that you don't really want. And what was more important here is the image scoring uh, of the different images performed by the radiologist that you can basically see here, and also lesion type frequency in different images. So basically considering the grounding class, opacities, crazy pathing, consolidation, nodular infiltrates, bronchovascular thickening, and pleural effusion. So the scores were basically so variable between 5 excellent quality and 1 interpretable. And the overall results associated with the assessment of image quality uh, basically demonstrated the feasibility of the approach and reaching approximately, so on the score side, 4.72, whereas the ultra low images were rated with the lowest scores, so around 2.70, 78. So more recently, so again, thanks to the colleagues for providing the data, the same author, so this is still unpublished work for COVID-19 segmentation of the lesions. So again, so CNN was basically trained using large databases for lung segmentation and COVID-19 lesion segmentation tasks. So basically the input is the CT image of a patient, and then this goes through a CNN, and the output should be the lung segmentations and the COVID-19 lesion segmentations. So you see here an example from the data were actually provided by different centers, and I'm not sure if you see the contours here. So obviously the manual delineation performed by the radiologist served as ground truth or as reference compared to the delineation performed by the AI segmentation algorithm. You see through the animation here that the manual delineation, both the lungs and the COVID lesions are in very good agreement on this 2D slice display. And if you want to see in 3D, so obviously see this is the manual delineation by the radiologist for 3 different patients. And these are the predictions. So you see that there is a good match actually between the AI and the reference or the gold standard, which is basically the manual delineation. You see this nicely, you see also on the 3D display here. So manual delineation, a very good fit with the predictions by the AI algorithm. So on the quantitative metrics side, so as you can see, I mean, the bias or the relative volume difference was actually very small. So depending on the center, so the performance was slightly variable. But if you take overall, I mean, the bias was really less than 1% with the small standard deviation And the same can be said actually about the intensities or the Hounsfield units. The second potential application here is basically building phantoms for the purpose of radiation dosimetry calculation. So both external, meaning X-ray CT, or internal from typical nuclear medicine examinations. Very good. So this is work done by Tian Wu from one of the postdocs in my group, recently moved to Shanghai, where he got a junior faculty position. So very briefly, basically, so the development of computational anthropomorphic phantoms went through different generations, starting from the 60s, where the human anatomy was approximated by sphere, then through mathematical phantoms, ICRP, the mirrored. In 2000, so the voxel-based models emerged, and then more recently, so the formable models using NURBS and other mesh techniques. And we expect that in the future, so we'll see the emergence of person-specific computational models, meaning that whenever you have the chance to go to perform your X-ray CT or nuclear medicine examination, so you can actually have your own phantom that can be used for patient-specific examination. So these models are extremely realistic, as you can see from this example here. So you really see the different organs, and we developed so a bunch of those models. Basically for modeling the features within the abdomen of pregnant patients at different gestation periods, and use this extensively in our research for radiation dosimetry applications. Obviously, when you look to the phantoms, you can imagine the amount of time taken basically to segment manually all the organs. So it takes really weeks and weeks of hard work by an experienced radiologist. So basically, the idea emerged: if we can automate the process of making those or building these models still for pregnant patients, and we use the UNet network in this context here to automate the processing of the data and be able to generate automatically the computational models. So what you see here is the original CT image, manual segmentation outcome performed by an experienced radiologist, and on the right side, so you see the outcome of the automated segmentation by the deep neural network. A small discrepancy that you see here, but overlapping the features in particular was very well delineated, and I guess you see this better on those two illustrations here for two different versions. Again, the manual segmentation compares well with the automated CNN or AI-based segmentation. Again, same can be said for the second example that you see on the right side here. But what was more relevant is basically the outcome in terms of radiation dosimetry calculations. And when you look to the results here, in terms of dosimetry calculations, when using the manual versus the automated segmentation, you see small differences here for some organs, but overall, I mean, the difference is quite small. If you look to the total body, actually, so we've got very good agreement between the radiation dose estimated from the manual versus the AI-based segmentation. There is also a trend in molecular imaging to reduce both the activity administered to patients to reduce the radiation dose and the acquisition time. And Zakharuk from Stanford, in a very nice review, predicted that in the future, so we might reduce the activity administered to patients for brain scans by 200 times, to reduce it to basically so the amount of effective dose that could be delivered to subjects for cross-country plane flight. And the same group, so from Stanford, did a very nice study. I guess we started working on this topic, so likely in the same time, but these they managed actually to progress very quickly and quicker than us, because obviously they are Stanford and they have 20 people, I think, on their paper, which is not our case. So what they did is that they basically used MR sequences to guide the synthesis process from the low count to the low count. So they decimated the standard dose cyanograms to a low dose cyanogram, and then they uses the learning procedure basically to enable the deep neural network to learn from the data. And obviously the MR was used as a support. And you see the outcome here. So very quickly, this is the full dose scan. This is the low dose scan on the right side, not really of diagnostic quality. And this is the output of the deep learning network with the MR as a support to the model, and without the MR. And obviously with the MR, the outcome was much better, as you can see from the qualitative assessments by experts, by radiologists. So you see that the full dose scan gets a score of almost 4.4 on average, and the PETs using the MR as a model to get the almost 4 compared to 3.2 using only PETs. So once the paper got published, so we needed to change basically the objectives of our study. And what we did is that instead of doing the implementation of the learning process in image space, we decided to do it in projection space, and we compared the two approaches, as you can see here. So the low dose to the full dose. So this was the first training, and this was compared to doing the training in the sinogram of projection space to enable the algorithm to learn how to generate full dose sinograms from the low dose sinograms. So we used this simple architecture, so a typical unit here. And then just to show you the outcome, so this is the full dose scan. We use a protocol where we basically inject around 200 megabecquerel for brain scans, and the patients, they wait about half an hour, and we scan them for about 20 minutes. So you see the full dose scan. This is the decimated low dose scan using only 5% of the counts. So equivalent to either injecting 10 megabecquerel, which reduces the radiation dose by a factor of 20, or scanning the patients in only 1 minute. All right, so the image is obviously not of diagnostic quality, and this is image using the deep learning prediction in the image space, and this is the deep learning prediction in a projection space. You see there's few artifacts, probably you don't see it well here, but we see it really on the console, so probably not the PowerPoint slide, but on the console you already see there's a small effect here, small artifact which is well compensated and dealt with the deep learning based reconstruction in the projection space. And here you see basically the bias or the difference images showing that the bias was also smaller when training the network in projection space. Just to show you basically some of the scoring assigned by our nuclear medicine physicians. So two of our co-authors did this work, and you see that for the low dose, for instance, they assigned scores of 1 for one study and 2 in another study, and full dose scans so assigned a score of 4. And in some cases, the predictions get a better score, as you can see in this example here. And these are the scores assigned by our nuclear medicine physicians. And so the implementation projection space achieved a score of 4.1, which is comparable to the 4.4 achieved by full dose. And obviously, so with the reduction of radiation dose by almost 20%, 80%. Some quantitative analysis. Obviously, you can see the paper if you're interested by this quantitative analysis. So for the sake of time, I'm just going to skip those slides here, but we have demonstrated basically that if you look to the band Altman's plots actually using the quantitative analysis for 83 regions from the Hammersmith Atlas, that in the projection space, so the outcome and the results were much better compared to implementation in the image space. So we got excited about the outcome and decided to continue this work, but for whole body imaging. So instead of the brain imaging that I just demonstrated here, so we extended this work to whole body imaging. And this is the outcome. So almost similar design study. You see the X-ray CT scan here, the full dose scan, the low dose scan, the predictions using two different neural networks. So residual network and cyclid again. And you'll see from the quantitative results that cyclin again basically outperformed the residual network, but obviously the image quality was quite similar to what was achieved by the full dose scan. And these are again, so the assessments performed by our nuclear medicine physicians. So we divided actually the whole body scan into two regions, the brain and the trunk. Basically, the trunk comprised the neck and the thorax and the abdomen of the patient. And you see that the scores specifically for the brain. So with the cyclid again, so for some reason, I mean, it's quite confusing, outperforming basically the full dose scan. So something that surprised us. And then for the second zone, you see that the full dose scan obviously so was the winner with a score of 4.78, and the cyclid again actually gets score of 388. So still very encouraging results. And more importantly, what we did here, so something that has never been reported in literature, is that we did really a full clinical assessment looking to the lesion detectability tasks, and we compared the number of lesions detected on the full dose scans compared to the low dose and using the two different networks. And you see that the cyclid again actually detected almost all the lesions except four. So very interesting results indeed, because you're not only interested actually in looking to the images and generate the same image quality, but we need to be confident also in the images that we generate in terms of lesion detectability. And luckily, I think we were quite happy with the outcome in this case. Again, so we've got some nice examples, as you can see here, where the full dose actually so depicted the lesion that was missed by the low dose and by the residual network, but the lesion was actually nicely pinpointed by the cycle again, and we got similar results compared to the brain scans when we use basically the plots that you see here. So another study here, basically, so using similar concepts again by the same PhD students, and again in collaboration with our Iranian colleagues. So the group of Professor I provided the data, and so similar strategies basically can be used also to reduce the time for myocardial perfusion scans, and this was explored so using two different frameworks. So the first is by reducing the acquisition time, and the second by reducing the acquisition time per projection. I guess you're familiar with the principles of MPI SPECT. And in the second example, so basically the idea was to reduce the number of projections, and then the deep neural network was trained for the prediction task, and this is basically the outcome displayed on short axis, long vertical axis, and long horizontal axis of the SPECT MPI, comparing basically the full time versus the full projections. And you see that the predictions actually produced very good results, especially when reducing only the acquisition time, and obviously outperformed the second approach where we reduced the number of projections. In another recent study, so basically in the context of PET's MRI, so we developed a novel adversarial semantic structure deep learning algorithm for MRI-guided attenuation correction in brain PET MR. So encouraged by the outcome of a recent comparative assessment, basically, so targeting the generation of pseudo CT images from MRI, which is yeah, almost the same problem that you encounter when you build an attenuation map for PET-MR. And so the outcome is that the DCNN, so an algorithm developed by Electra, so a company based in the US, so encouraged to push into this direction. And then we proposed this method that we called adversarial semantic structural learning, which contains basically two generative adversarial cores for city synthesis, what you basically see in the upper panel, and the semantic structure extraction, what you see in the lower panel. And the city synthesis core is governed by the L2 norm loss function for accurate city value estimation. So the semantic structure core exploits cross-entropy loss functions to maximize the fidelity of the generated synthetic CT to the target MR image. So for the evaluation task, we use the number of figures of merits, including tissue delineation, CT values estimation, and quantitative PET analysis. Let me just show you very quickly some examples here. So you see the MRI of the patient, the X-ray CT next to it, the segmentation algorithm into three tissue classes as performed by the software used in the clinic by Philips. So very rough approximation of basically two tissue class, soft tissue inside and air outside. And then the prediction by the deep learning, you see that the prediction works quite well. So prediction, even the skull, the nasal cavities. And if you look actually to the bias in percentage or the relative error, you see that the segmentation algorithm uh, results in a very high bias, especially in the nasal cavities and the skull, which is well dealt with the proposed network, as you see from this example here. Again, with the MRI reference CT that was used as a gold standard, and we compare so the to the atlas-based approach because it's used by some of the scanner manufacturers, especially from the brain, like General Electric and Siemens, and compared to the segmentation, which obviously ignores the skull and any bony structures that you have in the field of view. And we demonstrated through quantitative analysis, if you look just at the bias maps here, that the atlas-based technique, obviously, so in this particular case, brain imaging, so it's performed quite well compared to the deep learning approach. But the deep learning approach offers some advantages, but again suffers from outliers. I think we had one or two cases, probably only one, the one that you see here, where gross errors due to vulnerability to the input quality. So for this particular patient, impacted the atomical variations and the noise-induced bias, as you can see from this example, where the algorithm basically failed. So extending on the knowledge gained, so we used also deep learning guided estimation of attenuation correction factors. So instead of predicting the images, we predict the ACFs directly using time of flight PET emission data. So exciting work published in medical image analysis. So for the sake of time, I'm not going to go through details in this of the details of this work. So you can probably read the paper. It's kind of a bit complex to explain, but the outcome was really appealing and very interesting. Sorry, just drinking some water. So another work here. So a novel approach consists in using deep learning for joint attenuation and scatter correction again. So we started doing this work, and then there was a paper published in PMP by the group of University of California in San Francisco by CEO and his colleagues. And then again, so we changed a little bit the objectives of this study, so which happens frequently in science and in research. So we focused on multi-tracer neuroimaging studies. Basically, you know, so the principle of PET-CT, that you use the CT to correct the emission data for the photon attenuation effect, and this is how it's performed in the clinic to get the corrected attenuation corrected image. And so we wanted to basically move directly from the incorrected PETs to the corrected images directly by training a network with paired images. So we use the high-res nets in this context. And you see the outcome here for 4 different tracers that we use in our research. So basically FDG, you probably know FDG, which is the well-known and the working horse tracer used in dementia. And we use DOPA also, F18 DOPA for Parkinson's disease. And this was basically used for, I guess, if I recall well, about 50 studies, 50 subjects scanned in the context of a research protocol. and then a couple of other tracers. So basically, amyloid tracer and a tau tracer that we use also in our research. So basically, you see on the left side an X-ray CT, basically serving as a gold standard, and you see the PETs reconstructed with the CT-AC or CT-based attenuation correction procedure that we use in the clinic, compared to what can be achieved if you use the segmentation procedure that I mentioned earlier, basically consisting of segmenting the attenuation map into two tissue components. And then this is what is achieved by the deep learning-based training directly in image space for joint attenuation and scalar compensation. And if you look to the bias here, so basically the bias was much, much lower using the deep learning strategy compared to the segmentation-based approach, which is used actually in the clinic on our PET MRI scanner. And you see, so we had also a bunch of outliers, actually one per tracer, if you recall well, and just show you one of those outliers. So we basically have an overestimation for floor tosi-pair PET, where the deep learning algorithm failed, then we obviously have an overestimation of the tracer uptake. So we again extended this work. So again, in collaboration with the group of Professor I to do this for whole body imaging, with context of joint attenuation and scalar correction for whole body FDG imaging. And typically, so this is the deep residual network that was used in this context. I'm just going quite fast to be able to leave some time for questions at the end, and then we compare different options, basically on slice by slice basis implementation of the CNN network versus a bunch of slices. So basically 3D implementation, and the limitation was again so the memory on the GPUs actually to train the network, and the using also 3D patches. So 3D patches of 64, 64, and 64 located more or less randomly. And this compares so nicely the CD, PET CT AC, which means the PET corrected with this CT image, the non-attenuation corrected image that was used for the training. And these are the attenuation corrected images using the deep learning networks for the three different techniques that I just mentioned. And you see the bias maps here. Basically, there was some bias, but quite, I think, reasonable. So, given the approximations in the network. Um, well, obviously, so we've got also a few outliers. So this is one of them. By the way, so this clinical study took advantage of pretty large clinical databases that was used in this context. So this is one of the outliers here. And but the advantage of the technique compared to CT-based attenuation correction, well, in some of the cases, as reported in the literature, in about 20% of the cases, you've got a mismatch in the upper abdomen, in the thorax, because of the different breathing patterns, as you can see from this example here. So the deep learning reconstructions nicely recovers this because it's trained based on the non-attenuation corrected images. So it's nicely enables you to resolve these motion problems. So more recently, so one of my senior postdocs here in the lab, so Hossein Oradi, did a nice work in terms of transcation compensation metal dental implant artifacts reduction in the context of PETs MRI imaging. So basically, the just to show you the outcomes here in a few cases here. So you see the first case here on the left side showing you the X-ray CT. So we had the nice pairs of well-aligned X-ray CT and MRI pairs. And you see that basically this MRI didn't suffer from any truncation. Obviously, you know that truncation of the transactional field of view is one of the major issues that we face on PET-MR. So in this case, so we artificially simulated so the truncation artifacts to have access to gold standard for comparison, and then the deep learning network was used basically to learn from the image pairs, and you see the outcome of the Deep learning based compensation here. It worked quite well here. And you see basically, so from the arrows here, they depict the areas suffering from truncation. And this is another study here, another case with X-ray CT, the MRI, and the deep learning compensation of the truncation on the MRI. And you see the truncated attenuation map and the deep learning uh, compensation of this this attenuation map. And if the impact on the attenuation corrected MR images is obvious on this slide. And the same can be said basically for metal artifacts. You see the X-ray CT, the MRI, and basically the region corresponding to the metal artifacts, which obviously generates a void signal. So there's no signal in this area. And the deep learning based compensation did a good work in this respect, as you can see from this example here. And on the right side, you see another example with the X-ray CT, the MRI, and obviously the area here impacted by the deep learning and the outcome in terms of attenuation correction of the PET images. So you see some bias and some uh, issues in terms of image quality, and it has been shown also that the deep learning based compensation did a nice job in this respect. More recently, so interested also to apply this type of techniques for internal radiation dosimetry in the context of whole body imaging. So we used also a deep learning algorithm to predict the radiation dose actually delivered to patients from FTG. So we had a nice clinical database consisting of I think 12 clinical studies with dynamic data acquisition. And obviously, so for the sake of time, just show you a couple of examples here. So this is the density map used as input for training and also for the Monte Carlo simulations. And we basically compared the outcome of the deep neural network with the multiple S values technique developed recently by a group from Korea, and the conventional approach basically using a single S value as reported by the mirrored mathematical formalism. And you see nicely here, so the performance of the deep learning network. So in terms of, just to conclude this talk here and to give you the option to ask any questions. So I think we probably look into the number of articles published in the literature. We are probably facing a reproducibility crisis because most of the papers actually they do not give you access to the code actually used to produce the data. You don't have access to the algorithms on the clinical databases. And this is a nice survey actually published in Science recently on 400 AI papers presented at major conferences where only 6% included code for reproduction of the algorithms, and some 30% included test data, while 44% included pseudo code only. In terms of assessing so the relevance of research on AI for radiological applications, I think this is a very complex issue that need to be dealt with in the context of multidisciplinary teams that need to establish some guidelines. And I think the RSNA is very active in this respect. They published a number of guidelines on how to present papers actually for publications in this journal. And I think still a lot of work that still needs to be done. So I would like to basically thank my colleagues who did most of the work that I presented here. And I would also like to thank the funding bodies, basically Swiss National Foundation, European Commission, Eurostars program, and Qatar National Foundation for supporting our research. And with this, I thank you very much for your attention, and then I open the floor for questions. Any questions from the audience?
Hello, can you hear me?
Yeah, very well.
Hi, how are you, Habib?
Yeah, I'm
This is,
fine. How are you, Farshid? Good to hear from you.
thank you.
I
Thank you. Thank you
recognized
so
you.
much. Thank you. Thank you very much for your nice presentation. And so actually, I have a question, or let's say
Yeah,
challenge.
yeah,
Actually, you presented very nice papers and publications from physicist part. Do
yeah.
you think the deep learning will be well accepted by clinicians as well in near future?
Well, I think right now there is a clear resistance, especially from the radiologist. I mean, if just to share with you our experience, we have been discussing with our colleagues, radiologists, and we feel there is a resistance against the deployment of those techniques in the clinic. So they are very happy to be part of research projects, get involved in joint publications, of course. But when it comes to clinical adoption, not really a replacement of existing methodologies, but just actually to uh, as a kind of, as I mentioned, not a replacement, but something that adds on the workflow of what is done in the clinic. So we feel there is a resistance, and I think there is a similar trend worldwide where the MDs and the radiologists are still fear the impact of AI on their mandate and their mission. And hopefully in the future, so when they will feel comfortable that AI is not going to replace them, is and that the radiologist and nuclear medicine physician who masters AI is not going to is going to survive to the radiologist who doesn't master this field, and probably so they will feel more comfortable by in adopting these techniques and methodologies.
Okay, because I had some conversations with some physicians about deep
Yeah.
learning's application, and they
Hmm.
totally agree the application and the power of deep learning in research. But when I
Yeah.
asked them, okay, uh, what about reporting the images generated by deep learning? For example, for attenuation correction without any CT, if I provide some images to you with good correction, do you report it for a patient or not? And
Yeah. What was
let's
the answer?
say almost 100% told no,
They said
because
no. Yeah.
it
Yeah.
seems actually it seems not real image. We need real image for reporting patients.
Yeah.
I just have some concern that we put a lot of energy on deep learning, we put a lot of
Yeah.
effort in deep learning, but if the clinician not use them, okay, so
Yeah.
why?
Yeah.
Yeah.
Well, I fully agree, but I think there's something that probably the industry have studied carefully. I mean, we're putting our research efforts into this, so our grants and so it's public money, but the industry they are investing really a lot of money into this, and it seems they have groups of 200, 300 people working on their own base. So if they don't see, and they have people who have a good vision, and I think they're really strategic and see what will be the outcome. Not right now, but probably in within 5 or 10 years. And I think if they
Okay, can you hear me, Habib?
Professor Zaidi, we've lost your voice. I think maybe it's your microphone.
back my
Yeah, it's back on now.
Okay.
We still cannot hear you.
I don't believe they will.
Yeah,
Okay,
You
so
lost me again?
it's
now
okay
it's
now.
okay
It's
now.
okay now.
Okay.
It's okay?
So
Yep, yep.
you mean
Yeah, so
we
if
should
they don't,
you mean we can hope for next 5 years
yeah, I
to
think
be
so. I
okay.
think as a physicist, we need to do some lobbying. We need to do some lobbying and talk more and more to radiologists and nuclear medicine physicians to try to convince them. Yeah. So this is also part of our job. Yeah.
Okay, thank you very much, Habib.
Thank you,
Well,
Farshid.
thank
Yeah,
you very much,
nice to hear
Professor
from you.
Zaidi. And sorry, I couldn't unmute myself, and that's why there was a bit delay. So I would like to thank you once again for your amazing talk, and it was very interesting.
Thank you.
And it was good to see that there's so many Iranians working in your team, and maybe that's the benefit
Yeah,
of having a
that's
good
correct. Yeah,
student called Professor I, which now your students are working
yeah,
on AI, not
exactly.
AY.
Yeah,
I've
yeah,
got
yeah.
some,
Very
yeah, I've
thankful
got
to
some
Professor
questions
I.
as
Yeah.
well here. So before that, I can actually ask all of the audience in case if they want to raise their hand on the bottom menu, and we could actually give access to them for the microphone, and they could ask their questions, or
Yep.
also they could write the question in the chat menu, and then I would ask them from the professor. In the meantime, I've got a question. You had a very beautiful slide on the hype cycle. So where do you think we are on with regards to AI for on this hype cycle? Are we towards the beginning, towards the middle, or the end?
Well, what I just mentioned is so it was actually the hype cycle of 12, 18, and then deep learning was really on the top. Let me just try to find it. So it was, I mean, there is a company actually who did this type of surveys, and you see this is deep learning here. It's really on the top in the 2018, but for some reason, I mean, something that really disappointed and surprised me, because you can actually Google the hype cycle for 2019, and deep learning completely disappeared from the curve. So I don't really think that there is no hope for AI in the future. So yeah, probably some bias in the work that they did, but I still believe that AI is going to drive. So yeah, the technologies in the near future.
We have actually a comment by one of the audience,
Yeah,
and they're saying that they think neither AI nor DL is accepted by clinicians. And do you want to have add a comment onto that or not?
that AI or DLR will not be accepted.
By clinicians.
Yeah,
So
I will not
the
say this
traditional
way.
fight
Yeah.
between engineers and clinicians.
Yeah, so yeah, the PhD MD issue, I think we know this quite well, but I really see a lot of MDs actually doing research in AI, and I'll not really be formal in that way, so saying that it will never be accepted. I think we're still in gray zone, so it's not neither black nor white, so we're still in gray zone. I think it's up to us as physicists, as people who are working in this area, to do lobbying, as I just mentioned, so to convince our colleagues, not only by the number and the quality of the papers, but really trying to solve some day-to-day issues that they might face, demonstrating them. So on some examples, I might help them. And able to do this, we will manage to convince them.
Okay, thank you very much. I think your microphone's a bit, the connection's a bit
I
dodgy.
don't know
It's a
what's
bit,
going.
it's working now. It's working now anyway. I've got another question. So you mentioned very interesting data regarding use of deep learning or AI on image processing. And my question is, can we use AI or deep learning for actual acquisition, for coming up with personalized protocol for acquisition of the actual scan? Has anyone looked into that, or is that any
Yeah, excuse
use?
me, just lost you. Can you repeat the question, please? Because I lost the first part.
Okay, so the first part I was asking was your talk was on AI and deep learning on image processing and image sort of analysis.
Yeah.
What about moving a step back? Can we use AI or deep learning or any other similar tools for coming up with personalized acquisition protocols or imaging acquisition protocols? Has anyone looked into this, or is this any
Yeah.
use?
Obviously, I think I showed one example here where we basically, I mean, it's not from the analysis standpoint, it's really from the acquisition, trying to basically, so let me just find out the slides here. So what I showed here is really on the acquisition side. So what was done here is basically full dose scan corresponding to 20 minutes, and then decimating the sonograms to generate a low dose scan consisting of only 5% of the events, and then doing the training in the image and in the projection space to come up with the reduced acquisition time or reduced administrative activity. There is a lot of work being done also in the area of image acquisition. I just mentioned so this example here, but there are obviously a lot of studies reporting this type of issues.
There's another question just came right now. How are neural network models designed and developed? So, with regards to imaging and scans.
Well, I think this is a very general question that that there are different networks, and the different networks actually they target different applications. So in our group, so we focused mostly on cyclid GANs and on residual networks because they were appropriate for the applications that we are targeting. So basically for segmentation, for image translation, but there's obviously a lot of work being done basically by computer scientists in the area of in the development of new CNNs, and we need to learn from them and try to adapt those new networks to our applications. And obviously, so we need to pick up so those that are useful for the applications that we are pursuing.
Thank you very much. Again, if the audience, they can, if they have any questions, they can feel free to direct TPCF admin on the chat menu, and you can type your question or raise your hand, and give you access to your microphone, and you can ask questions. Another question actually I have is, so with regards to drugs, and that's sort of where I'm more interested in terms of the biology aspect of it. We usually have to test them on animal models. Do you think for coming up with use of AI or deep learning, is it beneficial if we actually first develop the models on animals and with different sort of injections and different acquisition times and parameters, and then come up with a sort of a really optimized AI model for it, and then move on to the clinical aspect of it? Do you think this is something we need to do, or we should just straight go to human sort of setting?
I mean, anything is in this area is obviously translational. So any research that is done in using small animals, rats and mice, and with the protocols that we can develop, so we obviously, this type of research is translational, and we can translate the knowledge, gain it from scanning small animals to humans. I mean, to the best of my knowledge, I mean, most of the research that is being done so focuses on humans, especially in terms of molecular imaging research. I mean, from the physics standpoint, for some reason, yeah, probably the paucity of large databases for small animals is one of the issues. I mean, most of the experiments they're carried out with probably less than 100 species. So if the data are available, so would definitely encourage this type of research. I mean, doing basically the investigation on small animal models and then translate these to the clinic.
Thank you very much. There's another question by Miss Zahra Mulaimanish, and she has asked, why use 5% in low dose? I think she's referring to this slide or the previous one. Why use 5% in low dose? Is it possible to use 1%?
Yeah, so actually this the paper that I just mentioned by the group of Shani Toll from Stanford, they used 1% of the activity, but actually, so it could be kind of misleading because you need to correlate this percentage with the amount of injected activity and also the acquisition time, also take into account the performance of the PET scanner used to scan the patients. Actually, in this study, so they used the Cigna PET-MR system, which had the higher sensitivity compared to the scanner that we use. and they injected more activity. So when we were attempted actually to use 1% of the activity, which would have been enabled us actually to beat this what they reported in this paper. But I think 1% is really below what we can afford. So considering that in Europe we inject less compared to the United States, because we inject about 200 megabecquerel and they inject about twice the activity in the United States. So 5% was kind of quite reasonable considering the activity that we administer to our patients.
Mhm. Thank you very much, Professor Zaidi. And there are some comments regarding they were interested on this talk. And I have to mention that this session was being recorded and it would be uploaded on the tpcf.ir website. I would ask the admin if she could actually write the website as well. So everyone could actually go to that website. And also, I have to mention we have our international bi-weekly webinars on the TPCF, and also we are running online journal clubs and courses. And so for all that kind of information, do visit our website tpcf.ir. And once again, Professor Zaidi, it was great to have you on this
Thank you so
platform.
much. Yeah.
Even though we're really looking forward to have you on the symposium, but I'm glad we had you here today, and we even had even probably a better session today evening, and hopefully see you soon on our
Sure.
future
Thank you so
events.
much. Please send me the link. I would be interested actually to follow the other webinars and to see what you're organizing.
Yep, definitely. Yep, cool.
Good. Thank you so
Thank you.
much.